Hello, this is Seth Schaefer of Team Just Cause Robotics, and today we'll be talking about my design for a 12-pound undercutter robot that I'm calling Draconid. This robot has a couple different purposes. First off, I wanted it to be at least semi-modular bot. I won't be swapping out weapons in between fights or anything, but the idea is to be able to reuse most of this chassis in a configuration that doesn't have a spinner on it, like probably a lifter configuration, so that I can fight it as a sumo-style lifter bot at Norwalk Havoc. And then the other thing I wanted to do is test out using brushless drive for the first time. Yet another was to have a fully 3D printable drivetrain, other than the tread, of course. And then my final main objective for this is to make it pretty much as low cost and yet still competitive as I could make it. So this isn't going to be like the most competitive robot out there by any means, especially in the full combat hobbyweight category, but it should be pretty capable, and the whole robot, even if you have tools to start with but don't have any of the electronics or any of the metal when you're starting, would cost less than $700 to build. So I'll probably include this in a link, but this is the bill of materials for the entire bot. As you can see, I have the motors for the drive and weapon listed as being the same motor because they are, and I have them as two separate items just to kind of show that. But essentially, the idea was to try and reduce cost as much as possible by using 3D printed gears and pulleys to generate enough of a gear ratio that I can drive the wheels at a reasonable speed using just low-cost brushless motors and no planetary gearboxes. Because when you're building 12 and 30-pound bots, often you end up using Bane bots or Versa planetary gearboxes, which can cost easily $60, $70, $90 a piece. And if you have 2 or even 4 of those in a robot, that pretty much sets your price floor at several $100s for just the drive system. Instead of doing that, I'm using motors that cost about $22 a piece. If you buy just one of them, I think it might be like 23 or 24, but motors are about $22 a piece, and they are these Race Star motors from a Chinese company, I'm getting them from Chinese website Banggood, which is pretty well known among drone builders. And these motors do not really have a particularly useful list of specs, but what they do tell you is that with a sizable propeller on them, they'll draw 25.5 amps, so I consider that to be the rated current for them. And then they are drawing about 566 watts at 6S when at 25.5 amps. So I'd assume that that's roughly, probably a bit lower than the rated power output for these motors. But what's nice about them is they'll run up to 8S, which means you're not really pushing their limits super hard at 6S, and they only weigh 142 grams. 142 grams is only 5 ounces each, so that means that you can have quite a number of these in a robot and have them add up to the weight of like one Harbor Freight drill motor, which is like almost a pound by itself. And then the BaneBots gearboxes, which are, mostly steel and aluminum, obviously are quite heavy compared to 3D printed plastic gears. So this not only reduced the weight of using an alternative solution by a lot, but it reduced the cost dramatically as well. So most of this robot's going to be made out of 6061 aluminum, pretty much all 1/4 inch and 1/2 inch, as you can probably tell. So the top and bottom plates are going to be 1/4 inch aluminum, and then all of the structural frame, other than this front piece here, are pretty much going to be 1/2 inch aluminum, which I pocket out on the CNC. So this is what the inside looks like right now. I don't have the ESCs catted in, but they weigh almost nothing. I'm going to switch back to the design view so you can see this more clearly. So I have the motors modeled in here, here, and here. And I kind of separated this into one like master CAD, and then I have the drive pods in a separate CAD component, because I designed those separately so that, like I said, I can kind of swap them between different robots in the future if I so choose, if these work out. So the idea is to get a bit higher than a 4-to-1 reduction through this drivetrain. Let me pull up just the drive pods to make this easier to see. So if I temporarily hide the outermost part, you can see all the gears and pulleys that are involved. So fitting these spacers in here was kind of a huge pain. It looks like this one's actually placed so that it might intersect with the wheel, so I might have to change that position slightly, but I needed to try and use some sort of screws with spacers to keep the two halves of the pod apart. So these are just 1/4-20 screws, and then a 3/8 inch aluminum round that I'm going to be drilling through on the lathe to make spacers, and they'll be used to basically clamp the two parts of this together. So this is like all armor, and not really that structural other than the points in between where the screws are. This is just internal structure. And then I'm using 1/4 inch shoulder bolts with bearings on them as a dead axle. And the nice thing about this is that all of these thread into the inner metal piece from the outside. So if I want to swap out a wheel or something, I can just take out this screw and pull the belt off and like swap out the wheel pretty easily without having to take the entire robot apart. I'm going to be trying to use these herringbone or like double helical gears as the main first reduction. So this is going to be, check again, that's about a 2-to-1 reduction from the gears. It's exactly 2-to-1 for the gears, and then slightly more than 2-to-1 from this small pulley to this big pulley. And then these are just sections of the same round belt, which I'm going to be using for tire tread probably. I might try just using a TPU 3D printing filament and 3D print like an actual kind of tire tread for these, but I think that this stuff is pretty grippy as it is, so it'll probably work fine on its own. So here you can get a better idea of what this reduction does. So this is showing the exact actual ratios and how they affect the rate at which things are turning. So the motors will obviously be spinning much faster than they're shown here spinning, but this tells you exactly how fast the wheels are turning compared to the drive motors. So the drive motors are 400 kV. I'll be running them at 22.2 volts, which means they'll be running at around 8,800 RPM. And that means I needed to reduce them to closer to like 1,500 to 2,000 RPM to be able to get the robot running at a reasonable speed, like not 40 miles an hour. So with this roughly 4-to-1 reduction, the robot should be going at a top speed of below 20 miles an hour, and it should be able to cross a 16-foot box in less than 2 seconds. So it's probably not going to be the pushiest bot, especially with brushless motors, but it's going to be very fast, which I wanted for eventually having it be kind of a control style bot at Norwalk Havoc when I have a lifter attachment on it. So back to the main design. You can see how I kind of pocketed out the top section, and I had to dogbone it because you have to have an end mill cutting these out that's round. So to be able to fit the top and base plates square against this edge, the cutter has to come out of that line, so that's why you see this like curve here. So the idea is that it's not just these screws keeping the top panel and the base panel from sliding side to side. It will be partly the actual metal from those internal side rails. And then the front and back and sides are connected to each other only via the top and bottom plates. So the reason I did that is because I previously had designed another robot with a kind of similar-ish construction out of plastic, which was called Conduit, and that was a 30-pound Sportsman bot that I brought to Motorama last year. And the problem that I had with Conduit is that I had the top and bottom all held on with screws like this, but they weren't screwed to the front and the back, they were only screwed to the sides. And then the front and back panels were screwed in from the front and the back respectively into the side panels. And this actually made it a nightmare to repair the thing, because in that robot the wheels were internal. So to change out like a wheel, if we had to do that, would have basically required taking the front and back and top and bottom off, as opposed to just like a side. So here with these drive pods as like almost separate pieces that are kind of bolted on only through the top and bottom, I have to take out 12 screws to get at them. And then if I really just want to change out a wheel, I only really need to take out this bolt, but if I have to change out any of the other gears, like it's still like 7 screws on one side, and that's not a big deal. And since they all thread directly in here, and they're just going to be compressing these spacers will tell exactly how far apart those panels are, and then these other spacers will position the gears and belts and everything as well as they need to be positioned, with just the belt tension kind of doing the rest. And it's basically just a much simpler and more straightforward way of making this like robust but still repairable. And having like, I mean, there's like a solid 1/4 inch steel shaft, solid 1/4 inch steel shaft, solid 1/4 inch steel shaft, and then 4 1/4 20 steel screws. So any like vertical spinner hit on here, I really don't expect to be like bending all of that, especially with the extra thickness that these 3/4 inch metal pipes are adding. So I think this will work out pretty nicely. Sorry, not 3/4, 3/8 inch metal pipes are landing. So inside, like I said, I have these two motors. I have them right now catted in so that I will basically have them slotted so that I can tension whatever timing belt I have. Originally, I wanted these motors further apart, and then I was going to have like an idler, like a bearing like sticking out from here. I might still do that, but trying to figure out exactly what length belt will wrap around something where it goes like this, then that, then this, and then that is kind of complicated. I tried to figure it out, and I have like sort of kind of a way of figuring it out by making this model here, which shows the shape that the belt's supposed to take, but I don't know for sure how accurate that's going to be to like real life, and I can't change the position of this because I want it to be threaded into the base plate if I'm going to do that. So I made it so that the motors are on slots so I can slide them individually apart from each other to tension the belt properly that way, instead of having to move the idler itself, because having a slot with a screw sticking up like that far from the base plate, because it has to be up like 1.5 inches, I would be afraid that the screw would start to like bend or be able to wobble around if it was slotted in and just had like a nut down there. And this is only a 1/4 inch thick plate, so that doesn't leave a lot of meat for the screw to grab, especially if it's like just tied on with a nut on the other end, on the other side. So it seemed much better to have screws that go into threaded sections. Using nuts in general is something that's like specifically mentioned as being a bad idea in the Robots Combat Robot tutorial. And the reason being that it's so easy to have them just like drop into your robot and then like get lost, or just it requires like 2 hands to tighten anything if you have to hold a nut with one hand and tighten with the screwdriver on the other. So it's just kind of a mess. So here shows the ratio that I've got here. These are going to be 24 tooth pulleys and this a 36 tooth. Other than using a timing belt, this is kind of similar to how Robert Cowan powered his weapon in Crippling Depression, though he used much beefier, more powerful motors and a V-belt instead of timing belt. But because I'm using a saw, and it's not going to be like stalling very frequently, using just timing belts seemed like a better idea so that I can get continuous cutting forces rather than having any slip from the V-belts on smooth pulleys. And then you can see there's something weird going on up here with this pulley. And why is that? So the saw attachment mechanism is something that I've spent a lot of time trying to figure out. So in trying to figure out how to attach the saw, I looked at two things, angle grinders and circular saws, as they exist as like normal power tools. Circular saws have a mount like what I've shown here. They usually have a screw with some kind of big washer, and then, let me just roll up the saw over here. They have a screw and some sort of big washer, the saw, and then another big like stepped shaft or washer, and then that shaft goes back with some sort of spline or flats or D on the end of it that connects to whatever is driving it inside the saw. In my case, I'm going to be using this big timing belt pulley. So I've designed this shaft so that I have flats on two sides that I can then have the 3D printed profile underneath this pulley just like slide down onto so that I have positive torque drive. But then I had another problem, which is preventing the shaft from dropping straight down. Originally, I looked at how angle grinders were secured, and I designed around this piece, which I found on McMaster. This is a slightly shortened version of it, where I just cut off some of the thread, but here, all angle grinders that use like 4.5 inch or bigger discs pretty much use a 5/8 by 11 threaded screw, and they have these like flange nuts that screw down that are threaded to clamp. There'll be like a washer here, and then the cutoff wheel, and then a flange that clamps down. The problem with that was that flanged nut needs to be somewhat thick because this is a coarse thread, so having like less than one thread wouldn't really work. And as you can probably imagine, I want my saw to be as low as possible to the ground. And I have literally like an 1/8 inch of tire sticking down below this part of my robot, so I already have to like pocket out the base plate to make it so that the saw can fit up in there. And that means that even just adding like a 32nd of an inch to how much lower than the saw my attachment needs to be is a bad time. So I realized that it would probably be best to just do it the way that all portable circular saws and most miter saws that I've seen do it, and have a screw that you thread into the shaft and have it be a smooth shaft instead of threaded. And the only problem this introduced was how do I prevent it from dropping straight down? So this screw up top into the top of the shaft through the pulley is just insurance, basically, to make sure that I have something preventing the pulley from pulling up and out. And then you can see I have a hex profile in here, and no, that's not because I'm expecting to get a hex head bolt in here. That would be ridiculous because you wouldn't be able to tighten it. That's actually to stick a 1/2 inch hex key into here so that I can hold the pulley in place while I tighten this screw to actually lock the saw onto the saw arbor, since without a way to hold the shaft still while tightening that screw, it'll just spin and it'll never get tight. So there will be like an 832 screw just holding this down, because that doesn't have to supply any of the torque holding, it only has to prevent this from pulling straight up, so it doesn't have to be a huge screw. All the torque transfer will be accomplished by the flats on the saw arbor, and then this hex will just be for tightening up and swapping out and loosening up to swap out the saw blade. And this is still a 5/8 inch shaft at the bottom, but throughout the rest of it, it's going to start as a piece of stock that's 1¼ inches in diameter, because that's the diameter of the thrust bearings I'm using here, or thrust bushings I should say. They're just oilites, and I'll be able to swap literally any commercial saw blade that's like 6.5 inches, or maybe slightly smaller ones on here. This is designed for a 6.5 inch saw, but it could take something smaller. And I might even be able to use like a 16th inch or 1/8 inch thick piece of metal as like an undercutter bar spinner if I so choose later. But of course that pushes this down further and I might not have the ground clearance for it. So that covers most of that. All this metal up front here is to support this plate and prevent the pulley from being disintegrated if a horizontal spinner that's higher than me, which most of them will be, comes over here to hit here. So this is all like beefy 1/2 inch, beefy 1/2 inch, and this is actually slotted into the front armor, so I can raise and lower this to accommodate different thickness saw blades, or like I said, if I want to put a bar on there or whatever, and I can make this as low to the ground as physically possible to try and get under other bots that have side armor with exposed wheels underneath it, to any degree greater than what I have here. Because as you can see, like, any robot with more than an 1/8 inch of ground clearance, basically, or with wheels exposed on their sides, I'll be able to rip the crap out of their tread with my saw, and that's kind of what I'm hoping to do to disable other robots. I'm not planning on, like, cutting through metal armor with these saws. There's, like, no way I'd be able to get the cutting pressure that I'd need for that with a robot like this. Then at the back, I have these forks. So these are literally exactly what they look like. They're just solid pieces of steel. There is a plasma cutter at the makerspace, which they are getting a CNC table up and running for, and I'm hoping to be able to cut these out on that from just some 3/16 inch high carbon steel. There's even a heat treat oven there, so I might even attempt to like harden or temper them slightly, but I don't think it'll really make a difference. The main thing that I want this to be able to do is to help me combat drum spinners and slightly combat horizontal spinners. Obviously, forks aren't the best for horizontals, but I don't have the weight or really like space or good attachment points for anything beefier than forks. And these will help me drive around and get under other robots in a control style manner. And they'll also work when the robot's inverted. So, for instance, if I was fighting against a horizontal spinner, what I would probably want to do, horizontal spinner. If I was fighting against a horizontal spinner that could outreach my saw blade, in other words, they'd be hitting here before I could touch their wheels, I might run upside down, run these forks against the floor this way because they're pivoted, so they'll just sit there due to gravity, and then I can drive the robot backwards as if it was controlled normally. And that way, I'm basically using this as the front of the robot to push them around and try and defend against the horizontal hits, hoping that they'll kind of deflect up off of these forks without hopefully nicking my wheels too badly in the back. And anytime I'm running in the forward configuration, if I'm going up against a wedge or whatever, I made it so that these front armor, or the sides armor, are offset towards the front. So they stick out to the front such that they completely hide the tread of the tire, so a horizontal spinner hitting me from the front can't cut the tread off of my tires here. But in the back, I intentionally left the tread sticking out along the entire back, so that if I'm pivoted up on a slant, I always have these tires contacting the ground. And that way, I should be able to get out of pretty much any situation. The only orientation that my robot would maybe be able to get stuck in is on the side, but I'm just going to add some sort of like 3D printed round segment, or maybe just a bolt sticking out. That'll make it so it just falls back onto its wheels if it's stuck on its side too. So that shouldn't be a big deal at all. So yeah, that pretty much covers all of the important design elements of this bot. If you have any questions, feel free to leave a comment, any suggestions as well. And I'll be hoping to come up with some sort of paint scheme after I start actually machining all the parts for this, but I'm going to be ordering all the aluminum soon, and I'll start posting probably some build progress videos or photos somewhere such that I can keep you all updated. Wait, before I go, I completely forgot to talk about the electronics, so let's get into that other than the motors. So in here I've shown this is going to be a 6S 1300 milliamp hour battery. It might be too small, I might go bigger later, but I'm pretty sure this should be adequate because that should allow me to draw an average of 26 amps throughout the fight. I don't think that my drive motors will be drawing an average of more than like 5 amps or so each, and the weapon motors maybe will be peaking at like 25 amps, but they probably won't be drawing more than like 10 amps or so continuous, so I'm hoping that will be enough to get me through a 3-minute match without any problems. If I have to go bigger, I should have some weight to play around with. Right now in CAD, my bot is sitting at 188.67 ounces. So that is 1.79 pounds. So I've got a little bit of wiggle room. All 4 ESCs that I'm going to be using are going to be 35 or 50 amp BL Heli 32 ESCs. They weigh like 10 to 15 grams each, like they'll add up to almost nothing. And then I also haven't modeled in yet the power switch, which is going to be an NBOTS power cutoff. I still have to figure out exactly where I want to attach that in here, but that will be done shortly before I start machining everything. I want to probably do a 3D printed like box for this battery and like maybe little layout boxes for the ESCs, but this isn't like 100% finalized, it's just like 95% done right now. And I can kind of put the ESCs anywhere. But yeah, I'll be using the BLHeli32s because you can easily program them to reverse, and that means I can use them for drive, and I can set different power limits on them for the weapon and whatnot, which will be nice to prevent these from like exploding if the saw is like grinding up against something hard and is almost stalling out the motors for too long. That would be really bad, so I want to have the ESCs set so that they can limit the startup current to the motors to prevent them from burning out. And that should allow me to get this all working quite nicely.